For voltaic cells, the difference in potential energy between the anode and the cathode, remember anode is where oxidation is occurring, cathode is where reduction is occurring. The difference in potential energy for these is called the cell potential. So the cell potential has to do with how likely, or how easily the anode will be oxidized and how easily the cathode will be reduced. The cell potential under standard conditions is called the standard EMF. So E and then the naught for standard and then the little cell and subscript. Of course, standard conditions are the typical ones we've been talking about, 25 degrees C, 1 atm, 1 molar concentration. For the overall standard EMF, we calculate this by adding up the cell potentials for the half reactions. So if you find out the potential for your oxidation half reaction, you find out the potential for your reduction half reaction, you add them together, that's your overall cell potential for the entire reaction. So now we're going to learn about cell notation, which is a shorthand version to describe a cell. So this is the structure of all of this. So we have an electrode and then we have a line. These single straight lines indicate a difference in phase. And what that means is you'll have a solid and a aqueous separated between this line. So typically the way that it'll work, and most likely for any of these cells, you'll have your anode on this side, and then you will have your cathode on this side. Your anode, you will have your solid first as your electrode, and your electrolyte will be aqueous. Obviously, electrolytes are aqueous now that I'm saying that. And then first you will have your aqueous electrolyte, and then you'll have your solid on this side for your cathode. So this is the pattern. So overall, I want you to really just grasp this pattern. If you do have any multiple electrolytes, I'll discuss that on a further slide where we discuss inert electrodes. In those cases, you will have multiple electrolytes, so you separate them with the comma. And then finally, this double line in the center indicates a salt bridge, so it separates the two half cells. And here we're just kind of tying it all together. This is the same example we discussed earlier, but now we have our cell notation at the bottom. So we have our anode over here, and we have our cathode on this side. And we can see how we are starting off with our solid, and then we go to our ion once it loses those electrons, and then we have our salt bridge, and then we have our cathode. It's starting off as an ion, turning into copper solid whenever it gains those two electrons. So I was hinting at this, but I didn't have anything actually written up, but this is what I was discussing. So typically your anode will be made of the same metal that you oxidize, and the cathode will be made of the same metal that you're producing. But in the case where you don't have that particular situation, you have to have an inert electrode. So it's one that doesn't participate in the reaction, but provides a surface for the transfer of electrons. So here we have an example of that. We have iron turning into, we have solid iron this time, turning into iron 2+, and then that's at our anode, and then we have our flow of electrons, and then we have our cathode on this side. Here is your cathode on this side, and our particular half reaction occurring here, our reduction reaction, is manganese in a polyatomic ion, and it's MnO4 minus going to manganese 2+. So it's starting off at a different oxidation number state, so +7 in the in the MnO4 minus, and then it's turning into just manganese 2+ ion. So you can see how it's being reduced, right? It's gaining 5 electrons total. So because it's staying as an ion, right? It's not turning into a solid metal. It's staying as that and then turning into another ion, just with the different oxidation number. You need an electrode that allows the electrons to be transferred, right? So what we use is platinum. It works really well. It's very non-reactive. It conducts the electricity you need, meaning it conducts the electrons. It lets the electrons flow. So we would notate this by putting a phase, phase difference line, and write our platinum after it as our electrode, right? Because it's solid versus all of these aqueous. So, this is supposed to be a minus, but here we have all our ions listed and just separated through commas for our cathode side. All right, so now we are going to put everything we've learned so far together, and we are going to write out a cell notation. So another way to say it is cell schematic. But we're taking a word problem and we're converting it to that cell notation. So we have a galvanic cell fabricated by connecting 2 half cells with a salt bridge. Okay, typical, we know that already. One in which a chromium wire is immersed in a 1 molar CrCl3 solution, and another in which a copper wire is immersed in a 1 molar copper chloride solution. Assuming the chromium wire functions as an anode, write the schematic for this cell along with the equations for the half reactions and the overall cell reaction. So if you want to, you can draw out the little picture and everything. But because I feel, hopefully, that you have that pretty strong in your mind of how the actual, laboratory schematic looks, we can go ahead and convert this into cell notation. So we know that we have chromium wire, meaning that's solid. So we have chromium solid wire, right? And it's inside a chromium chloride solution. So we know this is obviously a different phase, right? This is aqueous. So we're going to put a line, and then we are going to write the concentration, 1 molar CrCl3, aqueous. And that's it. That's our anode side. We know that our anode always comes first. And then we're going to write 2 lines to signify that is one side of our one side of our reaction, so that's half of your cell, and then the other half cell is your cathode side. So in this one, we have our aqueous solution that is turning into the solid. So this one is always the opposite. You always have your ions first, your aqueous solution first, because that is what is being leached. Those ions are being leached out and turning into the solid. So first you have your aqueous solution. For the other one, it's the opposite, because you're starting off as your solid, you're losing the electrons, it's turning into part of the solution. So that's why the chromium solid was first. But in this case, it's the opposite. So 1 molar copper chloride, aqueous, and then we separate it with the phase, and then it's copper solid. So it kind of looks like a mirror. Hopefully you start to notice the pattern if you do a few more of these. So we finished part of this problem already. We have finished the schematic, in other words, the cell notation. So what we're missing is the half reactions. So now we have basically our reaction here, even though it's not written out as a conventional reaction. But we can write out our half reaction. So we know our half reaction here, we know our half reaction there. if you know definitions, right, if you know that cathode is your half reaction for your reduction, and then your anode is your half reaction for your oxidation, that can get you pretty far. So knowing the terms is pretty important. So at your anode, meaning at where oxidation is occurring, we are starting off with our chromium solid, and we're turning into our ion, remember? So in this solution, this is an ionic compound, so when an ionic compound is in solution, it dissociates into its ions. So here, and I'm just going to write it off to the side just so that we don't have to, get confused with our little half reactions. But this in solution is basically this. And both aqueous. That looks horrible, but you get the point. Aqueous. So how do I know that it's 3+? Because this goes back to Chem 1. Chlorine, when it turns into an ion, is chloride. Chloride has a set charge based off its group. It's a halogen. Halogens, when they turn into ions, they have a -1 charge. Because I have 3 that balance out this cation, that means that this chromium had to have been 3+. It's a transition metal, so it can have various charges, but we figured it out. So it's like you use your known to get your unknown. So because of that, I know that's a long tangent, but because of that, I know that it's Cr3+, aqueous, and then obviously the 3 electrons that came off of it to get that 3+. So 3 electrons. And then we also have our cathode, where our reduction is occurring. And for this one, like I said, it's the opposite. And again, similarly to that chromium chloride, we have copper chloride. So when this turns into ions, when it dissociates, it's going to be copper 2+ aqueous plus your 2 chloride ions aqueous. So here we're starting off with copper 2+, and here is aqueous. Here this is reduction, right? So it's gaining electrons. So because it's going from ionic, copper ion, to solid copper, you need to make it neutral. So it's going to gain 2 electrons to turn into copper solid. Okay, now we have our half reactions. We have our anode and cathode. Now all that's left for you to do is add these. So luckily in none of this, we don't have any hydrogens or oxygens. If you don't have any hydrogens or oxygens, you can just directly add. With the exception of making sure that the electrons cancel out. So notice here we have 3 electrons, and I'm going to change my pen color. We have 3 electrons there. We need to make sure that those 3 electrons cancel out with these. Now obviously that is not going to cancel out. We need to multiply each of these. So I'm going to multiply this one by 2. I'm going to multiply this one by 3. And again, like I showed in a previous video, this is basically a coefficient, and it's carrying out in front of everything. And you get the point. So I'm going to rewrite that and add it all together. Okay, so I wrote everything on the reactant side, and then I wrote everything that we were adding on the product side, Notice anything that's the same on both sides is going to cancel, so we cancel that out, and what's left is your final reaction. So it's going to be 2Cr solid plus 3Cu 2+, gives me 2 chromium 3, and then 3Cu solid. So this is our overall reaction for this galvanic cell that we have. And again, just to mention this and repeat it again, this is a hard version of these problems. where you literally have to dig through it and, you know, figure everything out from scratch. And like I always say, I always give the hardest versions here so that the other ones, you know, in the test or the ones you practice on your own, hopefully seem a little bit easier. So, you know, don't be too, you know, scared or anything of these, especially because a lot of it is just terms, like if knowing cathode, anode, knowing other things like how these ionic compounds dissociate. It's a lot of things, but hopefully you're able to put it all together, especially using this as your guide, this example.